The first and most fundamental problem with the idea of humans permanently living on Mars lies in the physical and biological limits imposed by the planet itself. This is not a matter of slow progress or missing technology, but a confrontation with conditions that are fundamentally hostile to human life at the deepest level. Neil deGrasse Tyson often emphasizes that when we talk about colonizing Mars, we are not talking about moving into a slightly harsher version of Earth. We are talking about attempting to survive on a world that never evolved to support complex life as we know it, and more importantly, a world that actively dismantles the biological systems that keep human beings alive. Human biology is the result of billions of years of evolution under very specific conditions. Earth's gravity, atmospheric pressure, radiation shielding, day, night cycle, and chemical environment are not conveniences. They are requirements. From the structure of our bones to the way our blood flows and our cells repair DNA, everything about us assumes Earth-like conditions. Mars violates nearly all of these assumptions at once. The moment humans attempt long-term habitation there, they are no longer adapting to a new environment in a mild sense. They are fighting against physics and biology simultaneously. Gravity is one of the most underestimated factors in this discussion. Mars has only about 38% of Earth's gravity. This may sound manageable at first, especially when compared to the microgravity environment of space, but long-term exposure to reduced gravity has severe consequences. Studies from astronauts aboard the International Space Station show that even in carefully controlled conditions, humans experience significant bone density loss, muscle wasting, weakened immune responses, and changes in cardiovascular function. These effects occur after months, not years. Mars gravity is stronger than microgravity, but there is no evidence that it is sufficient to prevent these degenerative processes over decades or across generations. Bones, in particular, rely on constant mechanical stress to maintain their strength. Without enough gravitational load, bones release calcium into the bloodstream, becoming brittle and prone to fracture. Muscles follow a similar pattern, shrinking when they are not required to work against resistance. On Mars, this would not be a temporary condition. It would be a permanent state of partial physical decay. Exercise can slow these effects, but it cannot eliminate them. Neil deGrasse Tyson points out that we do not know if a human child born on Mars could ever safely visit Earth. The gravity difference might be so extreme that their body simply could not tolerate Earth's gravitational pull. At that point, Mars is not a colony, it is a biological trap. Beyond gravity, the atmosphere presents another nearly insurmountable barrier. Mars's atmosphere is incredibly thin, composed mostly of carbon dioxide, with surface pressure less than 1% of Earth's. This has immediate and lethal consequences for humans. Unprotected exposure would cause bodily fluids to boil due to low pressure, a phenomenon known as ebullism. Even inside pressurized habitats, the surrounding environment offers no margin for error. A small structural failure on Earth might be dangerous. On Mars, it is instantly fatal. Atmospheric pressure is also tied to oxygen availability and fire safety. Maintaining a breathable atmosphere inside habitats requires constant regulation, monitoring, and energy input. Any imbalance can lead to hypoxia, fires, or toxic buildup of gases. On Earth, our atmosphere is self-regulating through complex natural cycles involving plants, oceans, and microorganisms. Mars has no such systems. Every breath would be an engineering achievement, not a natural right. Radiation exposure is another critical issue that Mars cannot escape. Earth is protected by a strong magnetic field generated by its molten core. This magnetic field deflects charged particles from the Sun and cosmic radiation from deep space. Mars lost most of its magnetic field billions of years ago, leaving its surface exposed. Measurements from robotic missions have confirmed that radiation levels on Mars are far higher than what humans experience on Earth or even on the International Space Station. Radiation damages DNA, increasing the risk of cancer, neurological disorders, and reproductive harm. Over time, this damage accumulates. Neil deGrasse Tyson stresses that shielding against radiation is not a minor engineering problem. Effective shielding requires thick layers of material, often meters deep. This means that realistic human habitats on Mars would need to be buried underground or covered with large amounts of regolith. The popular image of humans walking freely under transparent domes is not supported by radiation science. Life on Mars would be hidden, constrained, and claustrophobic. Temperature extremes further compound these issues. Mars is cold, with average surface temperatures around -60 degrees Celsius. While temperature alone can be managed with insulation and heating, it increases energy demands significantly. Every watt of heat must be generated and sustained artificially. Unlike Earth, Mars does not have oceans or a thick atmosphere to distribute heat. Temperatures can swing dramatically between day and night, placing constant stress on materials and systems. Over long periods, this increases the risk of failure, and failure on Mars has no forgiveness. Then there is the question of water, the most basic requirement for life. Mars does have water, but mostly in the form of ice, often mixed with toxic perchlorates. Extracting usable water would require mining, processing, and purification on a massive scale. Water is not just for drinking. It is needed for growing food, producing oxygen, regulating temperature, and supporting hygiene. Every liter of water on Mars would be precious, recycled endlessly in closed loop systems. On Earth, water cycles naturally. On Mars, one mistake could contaminate the entire supply. Food production presents another biological challenge. Plants evolved under Earth gravity, Earth light levels, and Earth soil chemistry. Mars soil lacks organic material and contains chemicals harmful to plants and humans. Growing food would require artificial soil, controlled environments, and careful management of light and nutrients. Even then, long-term agricultural stability is uncertain. Any crop failure would be catastrophic. There are no surrounding ecosystems to buffer against loss. Psychological and neurological effects also deserve attention. Humans are social creatures adapted to open environments, natural light, and complex sensory input. Living in confined, artificial spaces for years or decades introduces risks of depression, anxiety, cognitive decline, and social conflict. Antarctica offers a small-scale analogy, but even there, people can breathe the air, experience Earth gravity, and return home. Mars offers no such relief. Neil deGrasse Tyson often reminds audiences that survival is not the same as living. A Mars colony might keep people alive, but at what cost to their mental and emotional health? Reproduction on Mars introduces yet another layer of uncertainty. We have no data on how reduced gravity, increased radiation, and artificial environments affect human reproduction and development. Radiation can cause genetic mutations. Reduced gravity may interfere with fetal development, organ formation, and bone growth. Ethically, experimenting with human reproduction under such unknown and potentially harmful conditions raises serious concerns. Without the ability to safely raise healthy generations, the concept of a self-sustaining colony collapses entirely. All of these factors together paint a clear picture. Mars is not just inconvenient or challenging, it is fundamentally incompatible with long-term human biology. Technology can delay consequences, reduce risks, and create temporary shelters, but it cannot change the underlying physics of the planet. Neil deGrasse Tyson's argument is grounded in this reality. He is not saying humans should stop dreaming or exploring. He is saying that dreams must be constrained by evidence. When people imagine Mars as a new home, they often project Earth-like expectations onto an alien world. But Mars does not negotiate. Its gravity will continue to weaken bones. Its radiation will continue to damage DNA. Its thin atmosphere will continue to threaten life with every structural flaw. No amount of optimism can erase these facts. The laws of nature are not impressed by ambition, wealth, or vision. They apply equally on Earth and on Mars. In this sense, the scientific impossibility of Mars colonization is not about rockets failing or budgets running out. It is about the mismatch between human life and Martian reality. Humans belong to Earth not by accident, but by deep biological alignment. Until we can fundamentally alter either human biology or planetary physics, the idea of Mars as a permanent human habitat remains a powerful story, not a scientific plan. When the discussion shifts from biology and planetary conditions to technology and energy, the idea of rapidly or permanently colonizing Mars encounters a different but equally unforgiving wall. Technology is often presented as the great equalizer, the force that allows humanity to overcome any obstacle given enough time and resources. Neil deGrasse Tyson challenges this belief by reminding us that technology does not exist in a vacuum. It must obey physical laws, energy limits, material constraints, and reliability requirements that become brutally strict when you leave Earth. Mars is not just far away. It is isolated in a way that magnifies every technical weakness into an existential threat. The first technological barrier is distance. Mars is, on average, about 225 million kilometers from Earth, but this distance constantly changes due to orbital mechanics. Launch windows occur roughly every 26 months, meaning that if something goes wrong, immediate rescue or resupply is impossible. On Earth, and even in low Earth orbit, technology benefits from rapid iteration, repair, and redundancy supported by a global industrial base. On Mars, you get one chance to get things right, and then you live with the consequences for years. This alone transforms engineering from a challenge into a gamble with human lives. Every piece of technology required for survival on Mars must be nearly perfect. Life support systems must operate continuously without failure, recycling air, water, and waste with extraordinary efficiency. On the International Space Station, life support systems are among the most complex machines ever built, and they still require constant maintenance, spare parts, and expert intervention from Earth. The ISS orbits only a few hundred kilometers above the planet, with resupply missions arriving regularly. Even under those conditions, failures and close calls are common. Transplanting this level of complexity to Mars with no rapid support pushes current engineering beyond its proven limits. Energy is the invisible backbone of every technological system on Mars. Without a stable and abundant energy supply, nothing else works. Heating, lighting, life support, water extraction, food production, communication, medical care, and manufacturing all depend on continuous power. Solar energy is often proposed as the primary solution, but Mars is a poor candidate for solar reliance. It receives less sunlight than Earth due to its greater distance from the Sun, and its frequent dust storms can block sunlight for weeks or even months. Historical data from robotic missions shows that global dust storms are not rare anomalies but recurring features of the Martian climate. When dust covers solar panels, power generation drops dramatically. On Earth, this would be inconvenient. On Mars, it would be fatal. Batteries can store energy, but storing enough power to survive long-duration dust storms would require massive infrastructure. Nuclear energy is another proposed solution, but it introduces its own set of challenges. Transporting nuclear reactors to Mars is expensive, risky, and politically sensitive. Operating them in an environment with extreme temperature swings, limited maintenance capability, and potential radiation exposure raises serious concerns. A nuclear failure on Mars would not just be dangerous, it would likely be unrecoverable. Even if energy generation were solved, energy efficiency becomes the next bottleneck. Every inefficiency translates into increased resource demand. Heat loss, air leakage, mechanical wear, and chemical degradation all consume energy. On Earth, these losses are absorbed by a vast and forgiving environment. On Mars, the system must be nearly closed, with minimal losses. Closed-loop systems sound elegant in theory, but in practice, they are extraordinarily difficult to maintain. Small imbalances accumulate, contaminants build up, and biological systems behave unpredictably over long timescales. Manufacturing and repair represent another major technological obstacle. A true colony must be able to build, fix, and replace its own equipment. Shipping every spare part from Earth is not feasible in the long term. This means developing advanced in situ resource utilization, using Martian materials to produce metals, plastics, electronics, and complex components. While it is theoretically possible to extract certain elements from Martian soil, doing so at industrial scale requires heavy machinery, high temperatures, chemical processing, and precise control systems. All of this demands energy, infrastructure, and expertise that must first be delivered from Earth. Neil deGrasse Tyson often points out that people underestimate how deep modern technology runs. A simple electronic device depends on global supply chains involving rare earth elements, ultra-pure materials, clean rooms, and highly specialized manufacturing processes. Recreating even a fraction of this capability on Mars would be staggeringly difficult. Without it, technological degradation becomes inevitable. Over time, systems break down faster than they can be replaced, leading to a slow decline rather than sustainable growth. Communication delays add another layer of complexity. Signals between Earth and Mars can take anywhere from several minutes to over 20 minutes one way. Real-time control or assistance is impossible. This means that Martian settlers must be highly autonomous, capable of diagnosing and solving complex technical problems without immediate help. While autonomy is admirable, it also increases risk. A single misjudgment or overlooked failure mode could cascade into disaster before Earth even becomes aware of the problem. Transportation on Mars itself is another underestimated challenge. The planet's thin atmosphere limits aerodynamic flight, while its rough terrain complicates surface travel. Vehicles must be robust, reliable, and easy to repair. Fuel production for these vehicles would likely rely on extracting and processing local resources, again tying transportation directly to energy availability and system reliability. Any breakdown in one area affects all others, creating a tightly coupled system where failures propagate quickly. Medical technology illustrates the limits of this approach starkly. On Earth, modern medicine relies on advanced diagnostic equipment, sterile environments, pharmaceuticals with limited shelf lives, and access to specialists. On Mars, medical facilities would be constrained by mass, volume, and energy limits. Many medications degrade over time, especially under radiation exposure. Surgical complications, infections, or chronic illnesses would be far more dangerous without the ability to evacuate patients or access a full medical infrastructure. Technology can reduce risk, but it cannot eliminate it. Neil deGrasse Tyson's skepticism is rooted in this cumulative burden of technological requirements. Each individual problem might appear solvable in isolation, but together they form a system of interdependent constraints that amplify one another. Solving one problem often worsens another. Increasing radiation shielding increases mass and energy demands. Expanding energy production increases maintenance complexity. Enhancing redundancy increases system weight and logistical burden. There is no free solution, only trade-offs that become more severe the farther you move from Earth. The idea of technological self-sufficiency on Mars also assumes long-term stability, yet space-hard, where degrades under radiation, thermal cycling, and mechanical stress. Materials become brittle, electronics suffer bit flips, seals fail, and lubricants break down. On Earth, these issues are mitigated through regular replacement and repair, supported by massive industries. On Mars, degradation is relentless and cumulative. Over decades, even the best designed systems will fail unless continuously renewed, a process that itself requires advanced technology and resources. In this context, Neil deGrasse Tyson argues that Mars colonization is not a question of ambition or funding. It is a question of whether technology can overcome fundamental energy and reliability limits in an environment that offers no forgiveness. At present, the answer is no. The technological systems required to support large-scale, permanent human life on Mars are orders of magnitude beyond what we have demonstrated in practice. They must work perfectly, continuously, and autonomously for years, using limited resources and operating in one of the harshest environments known. This does not mean that technological progress will stop or that Mars exploration should end. Robotic missions, scientific outposts, and short-duration human visits are realistic and valuable goals. But the leap from exploration to colonization is not a small step. It is a chasm defined by energy constraints, system complexity, and the unforgiving nature of failure. Technology, for all its power, is not magic. It cannot create abundance where energy is scarce, nor can it guarantee perfection in a world where mistakes are fatal. In that reality, the dream of a self-sustaining Martian civilization remains far beyond the reach of current science and engineering. A major reason the idea of rapid or large-scale Mars colonization persists is not because the science supports it, but because planetary science is often misunderstood or oversimplified in public discussions. Neil deGrasse Tyson frequently points out that Mars is treated in popular narratives as a backup Earth, as if planets were interchangeable real estate waiting for human development. This misunderstanding ignores how planets actually work, how they evolve, and how deeply Earth's habitability is tied to rare and interconnected processes that Mars no longer possesses. Mars today is not an unfinished Earth. It is a planet that has already run its course in terms of habitability. Billions of years ago, Mars likely had liquid water on its surface, a thicker atmosphere, and a more active internal structure. Over time, its smaller size caused it to cool faster than Earth. As its core cooled, it lost the magnetic field that once protected its atmosphere from the solar wind. Without that protection, charged particles from the Sun gradually stripped away much of the Martian atmosphere into space. This was not a sudden catastrophe, but a slow, irreversible process driven by planetary physics. Understanding this history is crucial because it reveals why fixing Mars is not simply a matter of adding technology. The planet's current state is the result of deep structural limitations. You cannot easily restore a magnetic field without reactivating a planet's molten core. You cannot thicken the atmosphere without a source of massive quantities of gas and a way to keep it from being stripped away again. These are not engineering challenges in the usual sense. They are planetary, scale problems that involve energies comparable to those that shape worlds. Terraforming is often presented as a long-term solution, but this concept is deeply rooted in science fiction rather than realistic planetary science. To terraform Mars, one would need to dramatically increase its atmospheric pressure and temperature. Some proposals suggest releasing carbon dioxide trapped in polar ice caps or underground reservoirs. However, measurements from Mars missions indicate that even if all accessible carbon dioxide were released, it would still fall far short of creating a breathable or protective atmosphere. The raw material simply is not there in sufficient quantity. Even if, hypothetically, Mars's atmosphere could be thickened, the lack of a magnetic field would remain. Without it, the enhanced atmosphere would continue to leak into space over geological timescales. Neil deGrasse Tyson often stresses that planetary habitability is not just about having air and water at one moment in time. It is about long-term stability. Earth has maintained a relatively stable climate and atmosphere for billions of years because of a delicate balance between its size, internal heat, magnetic field, plate tectonics, and biological activity. Mars lacks most of these stabilizing mechanisms. Another misunderstanding lies in the idea that humans can simply adapt to Mars. Adaptation in biology occurs over many generations through natural selection, and it requires that a population can survive long enough to reproduce under new conditions. On Mars, the conditions are not just different, they are actively harmful. High radiation levels increase mutation rates, but most mutations are damaging, not beneficial. Reduced gravity affects development in ways we do not fully understand, and many of those effects could be lethal or severely disabling. There is no evidence that humans could adapt into a stable Martian species without radical genetic intervention, which raises profound ethical and scientific questions. Swept into the river outflow, progress in science is not guaranteed to move in a straight line toward any desired goal. It is constrained by physical laws and diminishing returns. As systems become more complex, they require exponentially more effort to improve marginally. Creating a small, sealed habitat on Mars is one thing. Scaling that up to support millions of people is an entirely different category of problem. Planetary science tells us that scaling up often reveals new failure modes that were invisible at smaller scales. Public discussions often compare Mars colonization to historical exploration on Earth, such as crossing oceans or settling new continents. This analogy is deeply flawed. Every place humans have ever colonized on Earth already had breathable air, liquid water, Earth gravity, and a protective magnetic field. Even the harshest environments on Earth are mild compared to Mars. When early explorers failed, they could sometimes adapt, receive help, or integrate into existing ecosystems. Mars offers none of these safety nets. The planet is not merely hostile, it is sterile and unforgiving. Another key misunderstanding is the role of timescales. Planetary processes operate over millions to billions of years. Human societies operate over decades and centuries. Even if it were theoretically possible to alter Mars in beneficial ways, the timescale required would far exceed any reasonable planning horizon. Neil deGrasse Tyson emphasizes that proposals spanning thousands of years are not practical solutions for present-day challenges. They are speculative visions, not actionable scientific plans. There is also a tendency to frame Mars colonization as inevitable, as if it is the next logical step in human evolution. Planetary science does not support the idea of inevitability. The universe does not care about human narratives of destiny. Many civilizations in the past assumed that their expansion and survival were guaranteed, only to be constrained by environmental realities. On a planetary scale, Earth is extraordinarily rare in its ability to support complex life. Treating that rarity as disposable or easily replicated reflects a misunderstanding of how special our conditions truly are. Neil deGrasse Tyson often points out that when people claim Mars is our Plan B, they are implicitly assuming that Mars can be made more habitable than a damaged Earth. From a scientific perspective, this is almost never true. A polluted, warming, or environmentally stressed Earth would still have oceans, an atmosphere, gravity, and a magnetic field. Fixing problems within an existing, life-supporting system is far more feasible than building an entirely new one from scratch on a dead planet. This misunderstanding of planetary science also affects how resources are prioritized. Belief in an easy escape to Mars can create a false sense of security, weakening the urgency to address problems like climate change, biodiversity loss, and pollution. Tyson argues that this mindset is dangerous because it encourages avoidance rather than responsibility. Science shows that Earth is not replaceable on any meaningful human timescale. When planetary science is properly understood, Mars appears not as a future Earth, but as a cautionary tale. It shows what can happen when a planet loses its atmosphere, its magnetic field, and its ability to regulate climate. Studying Mars helps us understand the fragility of habitability, including our own. The scientific value of Mars lies in exploration and knowledge, not in fantasies of mass migration. In this light, the claim that Mars colonization is just a matter of determination or investment collapses. It is not determination that Mars lacks, but the physical conditions required for life. Neil deGrasse Tyson's critique is grounded in respecting what planetary science actually tells us, rather than bending it to fit inspiring narratives. Mars is a fascinating world, a valuable scientific target, and a mirror reflecting Earth's own vulnerabilities. But as a new home for humanity, it remains fundamentally incompatible with the realities of planetary physics and long-term habitability. The idea that humanity might one day abandon Earth and thrive elsewhere carries an emotional appeal, especially in an age defined by environmental anxiety and technological optimism. Yet, when examined scientifically, the notion that Mars offers a realistic alternative to Earth collapses under even basic comparison. Neil deGrasse Tyson consistently argues that the belief in escaping Earth is not only unrealistic, but dangerously misleading. The science shows that every problem we face on this planet is easier to solve here than attempting to recreate Earth's life support systems on a hostile world millions of kilometers away. Earth is not simply a place we happen to live. It is a finely tuned system that provides gravity, air, water, radiation protection, and a stable climate without constant human intervention. Even when damaged, Earth continues to function as a life support machine on a planetary scale. Mars, by contrast, provides none of these features naturally. Every element of survival there must be artificially manufactured and maintained indefinitely. From a scientific perspective, this difference is not incremental, it is absolute. Climate change is often cited as a reason to pursue Mars as a backup, but climate science makes it clear that even in worst-case scenarios, Earth will remain vastly more habitable than Mars. A warmer Earth still has breathable air, liquid oceans, fertile soil, and a magnetic field. These features do not vanish because of rising temperatures or environmental mismanagement. They may be stressed, altered, or damaged, but they remain fundamentally intact. Repairing and stabilizing Earth's climate involves changing human behavior, energy systems, and policies. Colonizing Mars requires rewriting planetary conditions that have been stable for billions of years. Neil deGrasse Tyson emphasizes that the scale of effort required to fix Earth is orders of magnitude smaller than the effort required to make Mars livable. Transitioning to renewable energy, restoring ecosystems, and reducing emissions are difficult political and social challenges, but they are not constrained by the laws of physics in the same way terraforming Mars is. On Earth, nature works with us. On Mars, nature works against us at every step. Water offers a clear comparison. Earth is covered in oceans, rivers, and underground aquifers. Even when polluted, water can often be cleaned and recycled using existing technology. On Mars, water must be mined from ice, purified, recycled endlessly, and guarded against loss. A single failure in water management on Mars could end a settlement. On Earth, water systems are resilient because they are part of a vast natural cycle. Science favors repairing a resilient system over building a fragile one from nothing. The same logic applies to air. Earth's atmosphere is self-regulating through photosynthesis, ocean chemistry, and geological processes. Even severe air pollution does not eliminate oxygen or atmospheric pressure. On Mars, there is no natural system to fall back on. Air leaks are fatal. Oxygen production must never stop. Carbon dioxide levels must be constantly managed. This level of fragility is not a sustainable foundation for civilization. It is emergency survival extended indefinitely. Food security further illustrates the imbalance. Earth's biosphere supports agriculture across diverse climates and conditions. Crops can fail in one region and succeed in another. On Mars, agriculture would exist in isolated, artificial environments with no backup. A disease, system failure, or energy shortage could wipe out food production entirely. Scientific resilience depends on diversity and redundancy. Earth has both. Mars has neither. Neil deGrasse Tyson also addresses the psychological dimension of this comparison. Humans evolved in open environments with natural light, weather, and biological diversity. While humans can endure confinement for limited periods, long-term isolation in artificial habitats introduces severe mental health risks. Earth, even when damaged, still provides access to nature, variation, and sensory richness that no Martian habitat can replicate. From a neurological and psychological perspective, Earth remains unmatched. Economics and resource allocation reinforce this argument. Every dollar spent sending resources to Mars yields diminishing returns compared to investing in Earth-based solutions. Building renewable energy infrastructure, improving water management, and developing sustainable agriculture on Earth benefit billions of people. The same investment on Mars supports a tiny, vulnerable population struggling to survive. Science does not support prioritizing the less efficient system when a far more effective one already exists. The idea of Mars as an insurance policy also misunderstands risk. A true backup must be independent and robust. Mars is neither. It depends entirely on Earth for technology, expertise, and initial resources. Any global catastrophe severe enough to threaten Earth's habitability would also disrupt the supply chains and knowledge base required to sustain a Mars settlement. In that sense, Mars is not a backup. It is an extension cord plugged into Earth. If Earth fails, Mars fails faster. Neil deGrasse Tyson often frames this discussion in terms of responsibility rather than limitation. Science does not say humanity cannot dream. It says that dreams must align with reality. The dream of Mars colonization can inspire technological development and scientific curiosity, but it should not distract from the urgent task of caring for our home planet. Treating Earth as disposable because of a distant escape option is scientifically unfounded and ethically questionable. From a long-term perspective, Earth represents a success story of habitability that we are only beginning to understand. Plate tectonics recycle nutrients, the magnetic field shields life, the atmosphere regulates temperature. Life itself shapes the planet in ways that promote stability. Mars shows what happens when these systems fail. Rather than seeing Mars as a destination, science invites us to see it as a warning. In the end, Neil deGrasse Tyson's argument is not anti-space or anti-innovation. It is pro-science and pro-reality. Exploring Mars expands knowledge and inspires generations. But the idea that it can replace Earth misunderstands both planets. The laws of physics, chemistry, and biology overwhelmingly favor fixing Earth over fleeing it. As long as Earth remains even marginally habitable, it will always be a better home than Mars could ever be. Science does not point us away from Earth. It points us back to it, with a clearer understanding of how rare, fragile, and valuable our planet truly is.